Hi, it's Ilya, and this is the third video in my VLA series. In the previous one, I talked about Pi0 from physical intelligence, and today we'll talk about more advanced version of this policy, Pi0.5. Pi0.5 is one of the best available open source VLA policies right now. And today I will cover following topics. We'll discuss what's the difference between Pi0.5 and Pi0. We'll talk about fast tokenization in more details. We'll discuss System 1 and System 2, and also some topics that were released after original Pi0.5 paper, like knowledge insulation or real-time chunking. Pi0.5 is built on top of Pi0, and I already provided a lot of information about this policy in my previous video. I didn't want to repeat myself, so I highly recommend to watch that video first before watching this one. And in this video, I assume that you already have knowledge about VLAs in general and Pi0. So let's begin. If you go to the physical intelligence website, you can see that after releasing Pi0, they released fast, they open source Pi0, they released iRobot, and actually these two components became building blocks to create Pi0.5. It didn't just appear from nowhere, it was a result of the extra work done after Pi0 released. Also, they released a couple more things afterwards. The first paper is about the knowledge insulation, and the second one about real-time action chunking. We'll talk about both of these things in this video, in addition to Pi0.5. And very recently, last month, they released Pi0.6 without the open weights yet. And this paper is mostly focused on the reinforcement learning approach to fine-tuning VLAs, and it's slightly outside of the today's topics, so I will not touch Pi0.6 today, but I will talk about everything else that happens between Pi0 and this real-time action chunking. In my previous video, I shared this schema of Pi0. It consists of VLM part that consists of two parts. The first one is LLM, that is Gemma, and the second one is the visual backbone, SIGLIP. And it can predict actions using two options. Option number one is to use fast tokens. Then we just have this VLM part that can output tokens after regressively. And option number two is to have flow matching action expert. That is another transformer that is connected to the actual LLM in the expert way. So it means that it attends to all the layers one by one. And using flow matching, it generates the chunks of actions directly from noise. If you want to move from this schema to Pi0.5, we just need to change the title, and that's it. So basically, Pi0.5 has exactly the same high-level schema. It has the same components. It has some very small changes in the way how attention mask works, or the way how the noisy actions are sent into flow matching. They change the logic a little bit, but fundamentally the schema stays exactly the same. Even more, I think the schema fits Pi0.5 even better, because Pi0.5 during training predicts both fast tokens and actions together. So you don't even need to choose between these two options. During the training, you can use both of them. Actions representation is one of the big open questions in robotics, and FAST solved this problem using a combination of discrete cosine transform and byte pair encoding. FAST is one of the main building blocks of Pi0.5, and I already touched it a little bit in my previous video about Pi0, and I even shown how to fine-tune the model using FAST, but I didn't go into details into the logic, how exactly this tokenization works. So now let's dive deeper and see how it actually works in practice. Before we go to more details how this discrete cosine transform works inside FAST, let's look at some more like visual examples. And the very widespread example of discrete cosine transform is JPEG compression. So this is very popular image format that probably everybody seen. And if you remember the time of very slow internet, then sometimes you may see that some websites are using progressive JPEG option, it means that it's kind of sends the first components of this cosine transform first. And what you would see on this website when image is loading, first you will see some kind of gray image, then you will see like very, very pixelated image, and then it will become less pixelated and you'll see more details, and eventually you will see the whole image. This algorithm of compression of sending data is very similar to what FAST is using. Yeah, so this is how it's used in Spec, but actually it uses, Spec logic uses 8 by 8 squares that you may see on the second picture. But it's maybe not so visual, so I applied the same logic to the whole picture that is treated as a one signal, and let's look how it works in this case. So the first step is the same, you get like just a gray screen. Then you're starting to see some general like colors that is used by image. Then I add more components, and now you see some shades on the image. Then I add more and more components, and now you can see some outline of my picture of this photo. If I keep adding more and more components, then the picture becomes like more and more clear, and you can see more and more details. And then you almost can see my face, and finally you can see the completely recovered picture. Fast tokenizer applies exactly the same math, exactly the same logic to the robot actions to make it work. So let's briefly look at the formulas and how it works in theory. So these are the formulas. They may look a little bit scary, but actually they're very simple. So let's look at it from actually bottom up. So the final formula that we care about is this one. So this formula takes our signal, that basically our actions in our robotics case, and represent our actions as sum of different cosine function that simply have different frequencies. And this is nothing but cosine functions multiplied by some coefficients, where alpha k is just some fixed coefficients depending on k, and they're not even trainable, or they're not like, they don't need to compute them based on the data, they're always the same. And xk is the coefficients that we need to compute. And to do it, we have this formula that actually looks very similar, but just the summation is done by k here, by n here. But generally, this is already a kind of solved problem, so you don't need to derive any of these formulas. You can just use them. And yeah, the idea is that like if you use this formula and apply it to your data, you'll get the coefficients that are simply the coefficients for the cosine functions. And if you sum up all these cosine functions with all these coefficients, you will get back your data. And this is the very simple idea. So let's look in practice how it works. Let's assume that we have some action chunk of like 30 actions, and for simplicity, we are looking at one-dimensional data. So in practice, we will have like different actions for different dimensions, and they will be combined eventually, but let's look at the one-dimensional example first. So I just generated some function that like looks like this, has some waves, and let's see what will happen when we start applying this discrete cosine transformation and sum up components and show them here. So the first component is always constant. It's the same as this like grayish background of the images that we've seen before. Then when we add like one more component, then we already have some shape kind of the signal that directionally says that there is some increase in the second half that kind of fits our original data. If we add a couple more components, it starts to fit better and better and better. So let's add another couple components, and now we almost fit our data. It's like already very good. And if it's actual robotics data and we don't really care about the dexterity, then it's probably already good enough to reconstruct our action chunk. But let's keep adding. So when we add 10, combine like 10 cosine components, then the fit is much, much better. After 20, it's almost ideal. It may even seem that it's ideal, but technically speaking, it becomes like absolute ideal fit only after 30 components. But again, you probably couldn't even see the difference between 20 and 30 because they are almost the same. Original 30 actions numbers, they're very different from what model usually predicting. So generally model LLM model predicts some tokens, and they have some sequence of tokens, and these tokens are different. So the token for the first representing like first word in the text, and the second and the third and fourth, they're very different tokens. In the case of actions, the model will need to predict very similar tokens many times in the row, or like very correlated values and so on. And there are like a lot of local minimums when, for example, it can start to predict the same values all the time, and it can generate a lot of problems in the training process. Another very important thing is that, as we already discussed, after 6 components, we already can reconstruct the whole shape of this action chunk. So we don't honestly need all the 30 components at all, and we can, in this particular case, we can compress our data from like 30 numbers to just 6 numbers representing the actions. And if we use just 6 numbers, we'll get really good enough approximation of the original action chunk. It means that we can effectively compress the information much better, and we can, instead of 30 numbers, use just 6 in this case. Let's look at all the coefficients that we computed for this chunk. And you can see that first 6 coefficients are very big, and they represent most of the signal. Then there is like a bunch of much smaller coefficients, and everything in the second half, the last like 15 coefficients, are very close to 0. When we apply fast, we also apply some quantization, and most probably many of these actions in the end will be quantized to 0, so they will represent by the same number. And effectively it means that we will be able to compress the information a lot. So on top of this discrete cosine transform, fast applies byte pair encoding. I will not discuss it here. It's very common way to tokenize in LLMs, and I will rather just send some link with a nice video about it. But yeah, the very simple idea is that this BPE goes through all the data that you have in training and looks at all the consecutive pairs of tokens. And if some pairs in your data are like very often together, then it simply replaces this pair of token with one new token. So this new token will represent a new pair. In our case, in case of kind of compressing the robotics data, we will have very similar pictures very often, and we will have a lot of the 0 tokens going after each other. So it means that probably after a few iterations of this BP, we will have token that represents, I don't know, 2 zeros, 4 zeros, 10 zeros, maybe 16 zeros in a row. And in this case, maybe like this whole tail of the last, let's say, 16 numbers will be just represented by one token. And eventually we will have like very good compression of the data. And this is basically how fast works. It allows you to compress the data in like very concise and very meaningful representation, where your tokens don't just represent one number, they represent the like whole cosine-like shape of your action. One important thing to mention that in general, there is no guarantee that you will have a lot of zeros in the end. Let's look at some fake example. I took the same function, I took the same action sequence, but I added extra like oscillation that happens every step. I added it artificially, so it's probably not very natural sequence, but let's look how it works right now. When we add 4 components, we have like general shape represented already correctly. When we have 10 of them, then it's pretty good fit, excluding these oscillations that we just discussed. But the problem is that even when we add another 10, so we move to 20, nothing changes too much. If you go to 29, it's still not changing too much. We see some of them became like closer. It's the whole curve is not so smooth, but we're still kind of far from the original data. Remember in the previous example, after 10, we were already very close. After 20, we were like almost exactly there. But here, even after 29 components, we see a lot of big gaps everywhere. And only when we add all 30 components, we get this exact fit. And also, if you look at the same chart, you can see that in the beginning we have very similar picture of the same components that are very, very similar. But now in the end, we don't have zeros. In the end, we have pretty big components too that cannot be ignored. And the reason why we have these components here is because I directly added this oscillation that has frequency of kind of 30 hertz. And this is why we see this big component here. In practice, if you look at the raw robotics data, I would say there is like very, very low probability that you have any meaningful signal that is coming under like very high frequency. So in practice, when you look at robotics data, you should see much, much more zeros here, because if you like teleoperate the robot, then your actual frequency that you as a human operate on is like much, much lower. You don't make like decision every like 30 times per second. But just take it into account, because, for example, if you apply some extra data transformation, like per-stamp normalization, for example, then you will introduce these changes that happening at every step. And per-step normalization breaks the smoothness of the curve that you're trying to use, and it will drastically reduce the compression of fast. So just make sure whenever you deal with the real robotics data and want to apply a fast tokenizer, make sure that you're dealing with the smooth trajectories and you didn't apply any extra things that can add this artificial signal on the high frequencies. Again, it shouldn't happen in the normal circumstances with the normal problem. To summarize what we've discussed so far, let's go to physical intelligence side and look at this schema. So how FAST works in practice. First of all, we have action chunk that is normalized, and here in this example has 2 dimensions. Then we apply discrete cosine transform that basically, similar to my slides, transforms this sequence of numbers into the coefficients of cosine components. Then they are quantized. You can see now that all these numbers are represented as some integer numbers instead of float numbers. And then important thing that I didn't mention yet is that when we have multiple dimensions, instead of encoding dimensions one by one, they kind of reorder the numbers and first take all the main components of each dimension. So they take like first component of each dimension first, then second component of each dimension, then third component of each dimension, and so on. And then eventually, like in the end of the sequence, you'll have most probably like a lot of zeros that will be combined together. And then finally, they apply this byte pair encoding that I mentioned. And if any two of these like numbers often follow each other, then they will be combined into one extra token that adds a lot of compression, and it allows to achieve very good compression and very nice and useful representation of action data. And after that, we have like many tokens, and these tokens are treated as any other tokens for VLM. You can also find a lot of actual examples how the robot works using this fast approach. The main drawback of using fast as is that it's slow during inference time. So during inference time, you need to generate all these actions one by one after regressively. And it's not the best approach because flow matching generates it faster. But it's opposite for the training. And you can see that in training, this, at least with Pi0, using fast is much faster, like 5 times faster than using flow matching. So it's very, very good speed up for training, but maybe not the best thing to use for inference because it's slower during the inference time. Also important thing is that this speed up happens when you train VLA from scratch. When you fine-tune VLA that's already trained on robotics data, it can be very different. And for example, in my experience, I didn't see any speed up coming from using fast. So when your VLA is already pre-trained, already trained for robots, maybe simple fine-tuning of Action Expert can be better solution than using fast. You can use fast tokenizer as part of OpenPy repository whenever you train model with fast, but also it's released and open source on Hugging Face, and you simply can use it as the tokenizer from Hugging Face even for other models, for your own data set, for your own data. Just simply a couple of lines of code and you can use it for any problem. Another interesting paper from physical intelligence is about knowledge insulation. This is the technique that allows to train VLA policy while preserving the old knowledge of the VLM that it was originally trained on. It technically was released after Pi0.5 paper, but if you look at the actual open source release of Pi0.5, then it's trained using knowledge insulation. So I think it makes sense to talk about it right now, also because it's very closely related to the fast tokenization. When we train Pi0.5, there are two losses and two sources of gradient. The first one is the one that coming from fast tokens, and it simply compares our predictions with the ground truth tokens, compute the loss, and then kind of back propagate this loss through the LLM and VLM part to update all the weights. And this is kind of pretty natural for LLM to predict some tokens and then back propagate the loss of these predictions to update the weights of all the parameters of the VLM. The second source of gradient is coming from the Action Expert prediction. Technically, flow matching predicts velocities of the flow process, and then we compare these velocities with the ground truth difference between the actual actions and the original noise. And this loss then generates a gradient that goes through both flow matching Action Expert and the LLM. And the problem is that, first of all, we initiate this Action Expert with random weights while VLM is pre-trained on the internet scale data. It means that when we start training the model, a lot of noisy predictions happening and a lot of noisy gradients go to VLM. Physical intelligence team mentioned that this actually impacts VLM, and VLM suffers from forgetting of the all information that it was pre-trained on when it gets such noisy gradients. I also can theorize that flow matching Action Experts is impacted by a couple of random things, like this random noise generated here and random time, so it can add a little bit of randomness and noisiness to the gradient. But again, the main point is that this part of the model generates a lot of noise, especially in the beginning of the training, and it degrades the quality of the biggest main part of the model, that is VLM. To avoid it, physical intelligence proposed what they called knowledge insulation. And the idea of it is just to not propagate gradient from Action Expert back to VLM. So what does it mean? It means that the part that is related to VLM only, including these fast tokens, is working as before. So nothing changes for this VLM part training. But for Action Experts, now it's different because the gradient that is coming from this actions prediction goes through the flow matching part, but doesn't go back to VLM. So whatever we predict here, whatever loss we compute here, whatever gradient we compute here, it doesn't impact VLM at all. And in this case, even if you start with completely random noise, if you have like very, very noisy gradients, they are not impacting VLM, and VLM never forgetting what it's learned before, or at least forget like much less. Also, this VLM can be trained on a combination of fast tokens and some text-based robotics-related questions and so on to generate like extra knowledge to make it better as a system too. It allows in one go kind of train two parts of the models completely independently. You kind of train VLM and make it more robotics oriented using fast tokens. And then your flow matching action expert just uses this VLM as is without changing it, and learns to attend to it and predict the correct actions. Based on physical intelligence claims, it speeds up the training of VLA 5 times. So that is a huge speed up. But I need to mention that it works only when you train the VLA from scratch. When you fine-tuning your VLA, or for example, you have already pre-trained Pi0.5 and you want to fine-tune it for your problem, I don't think you will get this kind of speed up because your model is already trained for robotics. You just need to slightly adjust the weights, especially weights in the action experts, to predict the actual actions for your robot. So I think this logic doesn't work as good anymore. And you will not see this 5 times speed up. But if you're training the model from the beginning, from the general purpose VLM, and using this approach, then again, based on physical intelligence, it's a very good idea and very good addition. Personally, I have some questions to this approach because I think in the paper they didn't provide the comparison with more straightforward, more classic deep learning approach where you just train the model in the 2 or 3 stages and you freeze some of the layers for these stages. So for example, in this case, what we could do alternatively, we could first train only using fast tokens, similar to how Pi0 is trained with fast tokens. And then we can add action expert and completely freeze VLM and train for a while the action expert part only. That is much smaller, so it should also be pretty fast. And then finally, we can have a third stage when we combine everything and train everything together without any freezing or any knowledge insulation. I don't know whether it would work better or not, but I would say it's more classic approach, how it's usually done with big neural networks. And would be nice to see some ablation or some comparison of this approach with knowledge insulation. But anyway, I see kind of the beauty of this knowledge insulation approach because you don't have any stages and don't need to think about freezing. You just run everything in one go and it trained much faster. So yeah, it definitely works and it's cool. But yeah, personally would like to see a bit more ablation if someone compares it with more classic approaches. And as always, you can find more information on the physical intelligence website. So you can see some examples of how it works. You can see schemas that show in what's exactly happening. You can see this animation and schema of how this corruption of VLM memories happens because of this noisy gradient from the action expert. And yeah, you can also see the results and improvements that demonstrated by this by knowledge insulation. And of course, I, as always, recommend you to read the original paper and find much more details there. Daniel Kahneman, in his book Thinking Fast and Slow, introduced concepts of System 1 and System 2 thinking. System 1 is the mode of thinking in which we complete some simple actions and that doesn't require a lot of reasoning. It's just something that we do automatically and we did probably many times in the past. And System 2 is something that requires us some reasoning, thinking, and it's more like slow mode that allows us to solve more complex problems. This concept was adopted in robotics community, and now you can often see the systems that have 2 parts, one for the slow reasoning and the second one for the actual execution. So System 1 that doing the actual execution and predicts action is often represented by VLA policy. And System 2 is usually represented by VLM model that can think about the original request, can do some reasoning, can split the problem into smaller steps that can be used as the input to VLA. I already touched this topic briefly in my previous video about MCP, where I allowed different LLMs to control this robot directly. In that experiment, I kind of skipped system 1. But in practice, all this approach of system 1 and system 2 really shines when you have like strong components for both of the systems. And this is what is recently often done with VLAs. So let's discuss how physical intelligence does it in the high robot work. And also, it's one of the main building blocks of Pi0.5. So let's talk about it. So imagine that you want to complete some complex task that consists of many sub-problems. For example, you want your robot to clean the room. And technically, your VLA model is able to do it because it can kind of move, navigate, it can grab objects, it can move objects somewhere else. So it was trained on this like smaller subtasks already. And there is kind of nothing that prevents it from being able to do it. But the problem is that it somehow needs to decompose the big problem into smaller subproblems. And this is where system 2 comes into play. And in case of Pi0.5, the same VLM, basically the same model, completely the same model, is used as system 2. So this model is trained to take complex problems and decompose them into simpler action plan. It can, let's say, in case of clean the room, it can say, oh, grab the white sock from the floor, move to the bin, put the sock to the bin, and so on. And these steps, every step of this plan, can be sent to the actual VLA, that again is just the same VLM model plus action expert. And this subtask can be used as an input. And then it works exactly as it works when it's separated from system 2. So this is the whole idea. System 2 is doing this slower thinking when it has complex problem and need to decompose it into simpler one. And system 1, that is VLA, just takes this command for a small task and simply complete this task. You run this system 1 and system 2 with different frequencies. So system 1 is predicting actions with 50 hertz frequency, and system 2 you can maybe like run it every second or every few seconds, or when the user interacts. For example, you can accept some correction during the task completion, and in this case, again, system 2 works as any LLM. So basically, if you take a picture of your room and send it to, let's say, ChatGPT and ask it to create the action plan how to clean the room, ChatGPT will do it. The only difference is that in this case, this VLM is specifically trained on this robotics task decomposition, and it's specifically fine-tuned for this type of problems. So it works very like nice and smooth together with the VLA part. As usual, if you go to the physical intelligence website, you can find a lot of examples and a lot of videos of robot doing the real things. And yeah, you can see example of this high robot when human provide original request, and then this system 2 splits it into some subtask, and then the robot actually completes this subtask. And kind of user can intervene at any point and give some extra information, and it will update on the go. You can again see more examples here, and if you look at the schema here, it will be more or less what we already discussed. So this system looks at the images and then high-level policy, system 2 in this case, take the prompt and take the current images to, first of all, generate some verbal response that is also kind of nicer because you can communicate with robot now, but also generate the low-level language command that goes to VLA. And then VLA policy also accepts joint positions and the same pictures and predict the actual actions that control the robot. I would also recommend you to read the paper and see that this approach improved results on different tasks. And also they show that this pre-trained model specifically for this problem works better than some other models like flat VLA or GPT-4o that probably was the smartest GPT on at that moment. So yeah, this like extra training on robotic specific data, extra training on like decomposing complex tasks into simple steps definitely helps to this system too. At this point, you should already know about Pi0, HiRobot, and fast tokenization. And to be honest, if you simply combine it, you'll get Pi0.5. I don't have too much to add on top of it. So let's just look at the official blog post and try to summarize what is Pi0.5 and how it works. As usual, Physical Intelligence website contains a lot of nice demo and nice videos. So here you can see how they brought the robot to completely new houses and let it do dishes and clean bedroom. And all of it is done using Pi0.5 as a policy. So it's very, very nice. Definitely watch it. It's very cool demo. Yeah, of course they have some other examples and they have like more explanations. So please read these things, read the paper that they share. I also want to show this schema that is very, very similar to what I shown on my slide. So they show that they use exactly the same VLM, exactly the same model. This model receives the high-level prompt. Then it predicts some subtasks. These subtasks are sent again to the same model, same VLM part, and then they finally generate continuous actions using the action expert. They also show all the data that they use for the training and kind of use code training on all the different types of data, both tokenized and not tokenized. When we have robot action data, we can train model to actually predict low-level actions, but at the same time we can have all these high-level predictions that either the like direct subtask commands that system 2 is supposed to predict, or some object detection, or some multimodal web data that can be related to completion of robotic tasks. So basically, whenever you kind of train it on the mix of data, you're not limited by using only actions as your target. You can use a lot of other internet scale data that can be useful for like developing the like reasoning in your policy. That is very cool. The next thing that I want to talk about is not directly related to Pi0.5. It's not part of this model, but it was released by Physical Intelligence a little bit later, and it's kind of improving the results of this model. So one of the big problems in chunk predictions is that these action chunks are independent from each other. And they're not necessarily connected, they're not necessarily combined into some smooth trajectory. And it can lead to some problems, starting from just the fact that the robot is like a little bit undecisive or shaking when it's completing the task, up to the actual performance degradation. And the solution that Physical Intelligence proposed is called real-time chunking. And it connects different chunks using the in-painting logic during the inference time. Let's quickly talk about real-time action chunking. So if you've seen my previous video, or you'll see like in a few minutes some demo from in this video, you will see that the robot is a bit of kind of jumping when it completes the task. So it takes some time to make the prediction of the chunk, then quickly execute this chunk, then freezes and make the next prediction, and then again moves, and then again freezes, and so on. So the trajectories that robot is using are not very smooth in the case of these heavy models when you take a lot of time to make predictions. This is problem number one, but the bigger problem is that you can have some multimodality in your data. So this is the case when you can do two different things. So you can go to the left, you can go to the right. And when you predict all your chunks independently and they don't know about each other, your model can end up in the case when it's simply cannot decide what to do and like just and switching between these modes all the time. And eventually it just wastes time or even like make some mistakes. So Physical Intelligence proposed to fix it by using in-painting. So the step one they proposed is that we actually should start to predict next chunk while the current chunk is still being executed. So if we start predicting like a little bit earlier, then by the moment when the first chunk is finished, we will already have the prediction for the next chunk. This approach has one big problem, that in many cases your chunks will get disconnected. For example, if you look at this image, so let's say the one chunk can go up, another chunk can go down. And if we started to make predictions here and make predictions for the second chunk, but continued to move as a first chunk, then we'll have very big difference between this step and this step, and it will probably make a robot to move very abruptly, and probably it will make it to fail whatever it's doing. So then the idea how to fix it is simple. So whenever we predict the second chunk, we need to somehow tell the model that our next actions that we are going to make are these actions. So model will not predict this chunk and rather will stick to another chunk. And this is exactly how it goes. So whenever we predict some chunks, some actions are frozen and we continue executing them. But the rest of actions are not frozen and can be updated. So these actions can be changed by the next chunk prediction. And then the rest of the actions is simply predicted from scratch. And eventually, like at each iteration, we have this overlap between two chunks that keep them at the exactly same values, so they never get disconnected. And the nice thing about in painting is that you don't need to retrain your model to actually apply it. So this is technique that usually applied in image generation. You probably have seen a lot of examples when you can kind of ask the model to repaint some particular segment of the image, or for example, take an image and ask the model to paint everything around this image, how to expand it. And this idea, this real-time chunking, uses exactly the same thing. It just sends first few actions as a initial kind of target for the model, and then model generate chunks that looks the same at the first few steps. And there are a lot of benefits. So if you apply this logic, then the throughput of your model is much bigger, and you can complete more tasks in the same time. Again, please read the paper and read this blog post to see how it goes. So I think there is two main benefits. First is that all the actions are more smooth and all trajectories are very nice. And the second, it actually works faster. It resolves multimodalities. It resolves potential issues when robot or policy can be undecisive, and so on. So yeah, read the paper. It's very nice and interesting. I think it's not yet open sourced in the OpenPy repository, but it's not so hard to implement if you want to use it in any other project. Also, you can see this little announcement that the follow-up paper was released for this real-time action chunking. As I explained, in the original real-time chunking, there is no change in the training process, and there is no change in the model, and only small adjustment in the inference. In this follow-up paper, they proposed the alternative approach where instead of changing inference logic, you change the training logic, and they simply condition the prediction of the action chunk by providing the first few actions. And the model during the training time learns how to predict these consistent chains of action chunks. But I will not go into details. You can always just open the paper and read about it. So they show that this approach shows a bit better results for the long latency, long delays. But also it has some cons because you need to change the training process, and also the first approach is much more plug and play. You don't need to change anything. You can apply it to the already trained model. This approach is constantly developing, so maybe in a couple more months we'll get better and better solutions how to deal with this action chunking in painting and other things to provide the consistent predictions. As usual, I will show a very simple demo using this robot. I trained it using a dataset that consists of 60 episodes with around 15 minutes combined length. And you can find it on my Hugging Face page. And also in previous videos, I provided much more details about dataset collection and how I use it. I show it just to demonstrate how it works in practice, and you can use the same approach to fine-tune the model, the policy, on your own dataset. But don't expect that you will see any generalization or language following or like all this nice demo like on the physical intelligence website if you're training or fine-tuning your model only on like such a small data set. So if you want all these benefits of the VLA with all the generalization, then you need to train your model on the hundreds of hours of teleoperation data with a lot of diversity across different tasks and maybe even different robots. I usually don't have such data sets for my personal robot. I don't want to spend hundreds of hours to collect data using this robot. But let me give a short spoiler of the next video. I recently participated in behavior challenge organized by Stanford as part of a new RISP conference, and our team took the first place. And in my next video, I will talk in details about our solution. And this is the case where we used a policy built on top of Pi0.5 that was trained to complete 50 different household tasks in the pretty realistic simulation. And in this task, we were given already the teleoperation data set with more than 1,000 hours of data. So this is the actual scale where all this generalization started to work, where some generalization patterns in the policy behavior finally emerge. So again, if you want to achieve such results, if you want this generalization, this is the scale of data that you need. And I will talk about it in more details in my next video. But for now, let's talk about how you can fine-tune the model in practice and how you can use it for the simple tasks like pick and place things using this robot. If you want to fine-tune Pi0.5 model yourself, there are a few options. Main option is to simply use OpenPy repository, that is official physical intelligence repository where they share different model, including Pi0, Pi0 Fast, and Pi0.5. You can see that Pi0.5 model that is presented here is trained using knowledge insulation, even so the original paper was released before the knowledge insulation. Also note that they don't currently support fast head for the Pi0.5 model. So you can only use and fine-tune using the flow matching head. But again, you can always just write this extra code yourself if you want to use fast logic for your model. The original code in this library is in JAX, but they also have PyTorch support. So there is some information on how to use PyTorch. And yeah, it's always up to you which type of the model to use. I prefer to stick to JAX and use the very original version. The alternative way is to use implementation of Pi0.5 from LiRobot. So they simply ported this OpenPy model into LiRobot, and you can natively train it inside LiRobot library. They have more information and all the code in the Git repository, so you can check it out. I didn't test it myself. Again, I just used the official implementation original in JAX for all my experiments, but yeah, you can also give a try and try to use the robot if it's more convenient for you. Also, you can find much more details about this repository and how to train the model and how to configure everything in my previous video about Pi0. And it's exactly the same. There is almost nothing changed, so I will not repeat myself here and just refer to my previous video to learn how to do it. Also, in my previous video, I shared the configuration file that I used to train Pi0 model. And the same file in the same repo that I have contains the config for Pi0.5 now. Again, it's exactly the same. You don't need to change anything in the training process comparing to Pi0. You just need to create the new config that specifies that you use Pi0.5 model instead of Pi0. And that's it. Basically, that's it. So it's very, very small change. If you already try to fine-tune Pi0, fine-tuning Pi0.5 is extremely easy. And honestly, I don't see any reason to train Pi0 nowadays, because Pi0.5 seems to work best and much better in all the cases. So whenever you want to train one of these Pi family models, just stick to Pi0.5 and use it directly. Again, as a part of my previous video, I shared this evaluation script that allows you to run JAX model and execute all the predicted actions on the robot using LiRobot. And as with all the configuration and everything, it's exactly the same for Pi0.5. So simply use the same file. The only thing that you need to change is the config name. So just use the name that corresponds to your Pi0.5 config that we just discussed, and everything will work out of the box, so you don't need to make any changes again. So if you already try to use it with Pi0, it will work with Pi0.5 out of the box with just a few changes in config. I've seen good results of this policy after just a half an hour of fine-tuning. So after just half an hour, it already was able to complete the task sometimes, and in all the cases did some reasonable steps. Currently, we are looking at around like 2.5 hours of fine-tuning, or around 5,000 steps of model fine-tuning on H100. I've been testing different models on the same simple task, trained on the same simple dataset. And so far, I think that Pi0.5 shows the best results out of them. In this video, you can see that it can consistently complete the same task again and again. It is doing it like 5 times in a row in this video until the first mistake. Sometimes it completes the task 10 or more times in a row. Mostly, it fails to complete the task when I put either ball or cap just a bit too far, and it's like slightly outside of the reach of the robot. Or maybe I just didn't have enough data when the objects are so far and it didn't learn how to deal with these cases. But in majority of cases, when the cap and ball are not so far, it works perfectly fine. Whenever I change the environment, it actually adjusts pretty well, because it doesn't have memory. It doesn't remember that the cap or ball was somewhere else. It just looking at where it is right now and simply adjusting to it, and eventually it can complete the task even if environment is changing. Also remember that this policy is stateless, so I don't use system2. It's just VLA policy directly. So if you want to apply it to more complex tasks that consist of multiple subtasks, you need a little bit more of engineering to make it work with system2. Here again, I just train it on one task and just want to show that it's able to control this simple robot. And also you may see that the movements of the robot are not very smooth. It's kind of shaking. It makes a movement, then it waits, and only then makes the next chunk. And this is exactly what RTC, real-time chunking, is fixing. Here, of course, it's not applied. It's just direct predictions from the VLA that are executed on the robot. Thank you for watching, and I hope you enjoyed it. I remind you that this is the ongoing series about VLAs, and I will continue to release new videos every few weeks whenever I have time for it. And if you have any questions about Pi0.5 or any other VLAs, please leave them in the comment, and I will try to cover them in the upcoming videos. Also, please like this video and subscribe to my channel if you want to see similar videos in the future. Thank you for watching. It was Ilya. Bye.